709 paper 3 and even in paper 1, the next type of question that you will find is figure out the nature of a stationary point. So what do we mean by nature of a stationary point? A stationary point is basically a turning point. So if it turns like this, the nature is that it's a minimum point. If the curve runs like this, then the turning point is a maximum point. And sometimes the curve appears to start turning but doesn't quite. So it might look something like this. This is called a point of inflection. Okay, so how do we tell, once we've found a stationary point, how do you tell whether it's a minimum point, a maximum point, or a point of inflection? So the basic rule for that is you take a second derivative. So you've already differentiated once to get the stationary point. Differentiate it again and find d squared y by dx squared. Right. Once you find that, you substitute the x value that you have found into this equation. And if d squared y by dx squared is greater than 0, then it's a minimum point. If d squared y by dx squared is less than 0, then it's a maximum point. Here it's kind of counterintuitive. Less than means maximum and greater than means minimum. And then d squared y by dx squared, if it is 0, then it's a point of inflection. I'm going to show you with some examples. So the first example is y is 2x cubed minus 3x squared minus 12x plus 4. Okay, so first we're going to find the x coordinate of the stationary point. So dy by dx is 6x squared. I'm assuming that you know how to differentiate. So minus 6x and then negative 12. So since it's a stationary point, we equate it to 0. Right, so we know it's some kind of turning point, equated to 0, and then we solve for this. So we end up with 6 times. You can use your calculator to find the factors, or you can do it manually. So this is what we end up with. Right, so x is 2 and x is negative 1. So there are 2 turning points. Now, what is the nature of these turning points? Are they minimum points or are they maximum points? So we do a second derivative. So second derivative. Okay, so d square y by dx squared. We are differentiating this. So we get 12x minus 6. Okay, so now we don't equate this to 0. Instead, we substitute each of the values of x into it. So x equal to 2 and x equal to negative 1. So for x equal to 2, d squared y by dx squared is 12 into 2 minus 6. It's 24 minus 6, which is 18. 18 is greater than 0. And according to the rule we have up here, if it is greater than 0, that's this, it's a minimum point. Therefore, minimum point at x equal to 2. Similarly, plug in the value of x equal to negative 1. You get 12 into negative 1, negative 6. That's negative 12, negative 6, which is negative 18. And that is because it's less than 0, that's a max point at x equal to negative 1. With inflection, so y is equal to x cubed minus 6x squared plus 12x minus 3. Differentiated, so dy by dx is 3x squared minus 12x plus 12. And to find the stationary point, we equate it to 0. This gives us, when you put it into your calculator and solve it, it gives us x equal to 2. So we know that there's a stationary point at x equal to 2. We're trying to find the nature of that stationary point. To do that, for nature, we always differentiate it again. So d squared y by dx squared. We're differentiating this. So we get 12x minus 12. Sorry, not 12x minus 12. We get 6x minus 12. Now we don't equate it to 0. Instead, we plug in the value x equal to 2. And we get 6 into 2 minus 12, which is 12 minus 12, which is 0. That tells us that this is a point of inflection. So just to reiterate, if d squared y by dx squared with the x value of the stationary point plugged in is greater than 0, it's a minimum point. If it's less than 0, it's a maximum point. And if it's equal to 0, it's a point of inflection.